All right, big ideas, Algebra 2, Section 4.3, dividing polynomials. So we're going to use long division to divide polynomials by other polynomials, use synthetic division to divide a polynomial with a binomial, and then be able to use the remainder theorem. So dividing two polynomials using long division is very similar to the way that we use long division back in elementary school when you have very large numbers to use long division. You're trying to think of things that multiply by the number on the outside or by the term on the outside that gets you what's underneath or in the dividend. So at the end of each stage, you'll then be able to divide that term by the highest power to figure out what's left over after that first term is canceled out. So that's going to keep giving you the next term. So when we're dividing these two polynomials, the first thing that we're going to look for is something that we're going to put up here that we can multiply times x squared that will give us 2x to the fourth. So that's what we're going to then do the opposite. Something times x squared equals 2x to the fourth, and that something is 2x squared. So that's going to go up above however many terms are on the outside. So there's 3 terms on the outside, then you're going to count 1, 2, 3. It's going to be above the third term. Also make sure that you have zeros for any terms that you may be missing. So notice how there are no x squareds in this dividend. You have to put a 0 there so that you're making sure all of your terms line up. So then you're going to take your 2x squared, multiply it times all 3 of these terms to get this blue line down here at the bottom. Notice how, again, that these two line up with each other, line up, all the terms are equal. And the first ones are the ones that are going to end up canceling out. Because the next step is to then subtract 3x to the third minus 6x to the third is your negative 3x to the third. 0 minus 4 is negative 4, and then 5 minus 0 is just 5, and then you're keeping all of your terms there. Then we're going to repeat this process. So some term up here times x squared, that's going to give us a negative 3x to the third. So we need to multiply an extra x and a negative 3 so that they line up. So that's a negative 3x. Multiply that negative 3x times everything and line up your terms. Subtract, notice how these two are the same, so they cancel. Negative 4 minus a negative 9 is positive 5. 5 minus a negative 6 is positive 11. Bring down your negative 1. And then for the final term, you're going to think of something times x squared to get 5x squared, which is 5. Multiply everything down there. Subtract. And then you're left with a remainder because there are no extra terms over here on the end that can be brought down. So when you divide these two polynomials, you get 2x squared minus 3x plus 5 with a remainder of negative 4x minus 11. And here's how you're going to write the remainder. So this is what the answer up at the top is, or your quotient. Your remainder is going to be set up in a fraction where the remainder is the numerator and your denominator is the term that is being divided by. Kind of similar to how you did remainders for long division. You ended up using mixed fractions, so you had a whole number plus some other fraction with the remainder on top. Now we can check this by then multiplying backwards. So if 2x squared minus 3x plus 5 times all of this plus your negative 4x minus 11 gives you the result of what we got at the top. So we're multiplying those two things and then adding our remainder at the end using double distributive property, like what we did in the last section of multiplying polynomials, and then combining like terms, and that is end up what you got from the beginning. So it's a good check to make sure that you're getting the correct answer both forwards and backwards for dividing and multiplying. All right, so instead of using long division, if keeping all of your terms constant, using synthetic division could be something that would help you keep everything all together. So rewrite your terms so that you only have the numbers. You have your negative 1 for your x to the third. You have your 4 for the x squared. Remember that you're keeping the zeros in your x term, and then your 9 right here at the end. The number that you are being divided by, so long as it is a binomial, is always going to be whatever number your x is being subtracted by. So since it is x minus 3, we're going to take this positive 3 and use it as this k value to the left of this bar. Okay, so that's the setup. Then you're going to bring down your first coefficient. So bring down the -1, multiply your k value times that -1, and then you're going to write it underneath your second coefficient. So the -1 gets brought down. 3 times -1 gives you this number underneath your second coefficient. And then you combine these two by adding. Normally in long division, we would subtract. With synthetic division, you're adding because you're including your positive and your negative numbers. So it's more of like a combined like terms. And then you're just going to keep repeating that process with what you got. So you're going to take your k value, 3 times 1, write it here underneath your next coefficient, add 3 times whatever that number is underneath your next coefficient, add, and you're just going to keep repeating that process until you filled out all of your coefficients in that second line. So we had our 3 times 1 to get 3, adding these two to get the 3. 3 times 3 is 9, adding those together to get your 18, and this last number is your remainder. So if this number is 0 at the end, you do not have a remainder. Okay. Now, whenever you're rewriting this in terms of your terms, you're going to start with one that is 1 less than what you started with. So your -1 becomes -1x squared because you started with an x to the third. +1 becomes an x because that is in the next order of standard form. 3 is the constant by itself, and then 18 is your remainder divided by what we originally started with in our division. Let's try another one with synthetic division. So because this divisor is x plus 1, we're going to switch the sign and use -1 as our k value. To set it up, you have a 3, -2, 2, and -5, similar to the coefficients up here. And then you're just going to repeat the process of bringing down, multiplying, bringing down, multiplying, bringing down, multiplying. So bring down the 3 times -1 is -3. Combine to get -5, multiply to get +5, add to get 7. -1 times 7 is -7, add to get -12. So this is our remainder. We started with an x to the third term, so this becomes 3x squared minus 5x plus 7. Don't forget to include your remainder divided by the original thing that we were dividing it by. All right, so using the remainder theorem, so if a polynomial is divided by your x minus k, which is that number that's outside the synthetic division, then your remainder is equal to r equals to the function of k instead of function of x. So it tells you that the synthetic division can be used to then evaluate a polynomial function by plugging in your k so long as you are dividing your x minus k. So using the synthetic division and then evaluating when your x equals -4. So we are going to actually be plugging in -4 because we're not dividing by a polynomial. And this will help tell us what the value of that is using the remainder. So again, pulling out our 5, -1, 13, and 29 from our coefficients up here. Bringing down, multiply, add, bringing down, multiply, add will give us a remainder of -359. So using the remainder theorem, you can conclude that evaluating this polynomial function at -4 is a value of -359. So we can check this by just substituting in -4 into our original function in the x. So you have -4 to the third power, -4 squared, and then -4 times your 13. After you use all of your exponents and you're multiplying, you get -320 minus 16 minus 52 plus 29. And hey, look, when you combine those together, you get the same thing as the remainder of synthetic division. So remainder theorem works not only for determining your remainder, but for evaluating a function at a specific value.